Okay, I think we can start the first session of this afternoon. Professor Wegman from George Mason University will show us methods for visualizing data.
I noticed she left off high dimensional, so after David and others are talking about, Sarah is talking about 10,000 dimensions. I'm sort of, maybe I should call it medium dimensional data. So let me tell you, we've been trying to do this visualization stuff for a number of years now, and we've kind of come to a number of techniques that we found to be useful. We talk about parallel coordinates, and that's been around for a while, but we have some alternate interpolations. So I want to talk about those a little bit today. We also talk about grand tour, using that in conjunction with parallel coordinates. And so I want to tell you a little bit about how we do that as well. I have some illustrations. If we have time, I'll show you some of the illustrations towards the end of the discussion. So this is the basic agenda that I'd like to work on today. And as I was saying, we use three of these techniques in combination with each other. Parallel coordinates is a pretty effective method for looking at high dimensional data, where of course high dimensions means multiple attributes. When we were thinking of this, practically speaking, I've used this with visualizing up to about 130 dimensions or so. Certainly not 10,000 dimensions, but maybe 100 or 50 dimensions is not so hard to do. We use this in conjunction with the grand tour idea, and I'm going to try and explain the grand tour and some variants of the grand tour that we do. The other thing we talk about is the idea of saturation brushing. One of the problems with computer graphics is that if you have a lot of data on the screen, which I guess for small n is not such a problem, but anyway, if you have a lot of data on the screen, you get a lot of overplotting, and so it's very hard to distinguish individual pixels when you have so much overplotting. So I'm going to try and describe all of these to you. The basic notion with parallel coordinates is that if you try and do a Cartesian plot, you basically fail after 3 dimensions, because we don't have, at least in this visible world, more than 3 orthogonal dimensions. So the fundamental idea is to give up the orthogonality and draw the coordinate system as a series of parallel axes which can be placed in a plane. The idea then is to plot a point in high-dimensional space, in multi-dimensional space, as a polyline, and I'll show you how that works in a second. And it turns out when you do this, it's a unique representation of the point in multi-dimensional space. In essence, except for real estate on the computer screen, the number of axes is essentially unlimited, so the dimension is not really so much of a problem. Now this is the basic idea. If we have a Cartesian plot here on the left-hand side, we have a point A and a point C, and those 2 points determine a line. The way we do this in parallel coordinates is we draw an axis for the x-axis and we draw an axis for the y-axis. We plot A on the x-axis, A and 0, and on the y-axis we plot MA plus B and 1, and we join those by a line. So the point A, MA plus B, is represented by this line in the parallel coordinate display. At the same time, the second point, C, is plotted as C0 and MC plus B and 1. And the fundamental, the really intriguing notion is that these 2 points determine a line in Cartesian space, and these 2 points correspond to 2 lines in parallel coordinate space, and their intersection determines a point in parallel coordinate space. That point is in one-to-one correspondence with the line in Cartesian space. So we have a really kind of nice duality. In Cartesian space, lines map, points in Cartesian space map into lines in parallel coordinate space and vice versa. So there's a fundamental projective geometry duality in this representation. Points map into lines, lines map into points. There's a lot of other dualities that follow from this. For example, circles and ellipses in Cartesian space map into hyperbolas, what are so-called line hyperbolas in parallel coordinate space. And so it's relatively easy to diagnose a circular or elliptical structure in parallel coordinate space because you have basically a hyperbolic shape. There's other interesting dualities. Rotations in Cartesian space map into translations in parallel coordinate space and vice versa. And one of the interesting things is that points of inflection in Cartesian space, which are relatively hard to diagnose, map into cusp in parallel coordinate space, and so cusp are relatively easy to see. So a fundamental idea is that these dualities allow a relatively easy interpretation. Things that you see in Cartesian space, you can also see in parallel coordinate space, but parallel coordinate space has the advantage that you can stack up the coordinate axes, and so you can see higher dimensional structures. So in particular, a set of points with slope 1 will map into a set of lines that are parallel, and a set of lines with slope -1 will map into a set of lines that have a common intersection. In projective geometry, that's typically called a pencil of lines. It's often much easier to detect negative slope than positive slope because of the common intersection. And so one of the things that we are interested in doing is showing some of those things. Now I'm going to talk about how we do the parallel coordinate stuff and how we do the Grand Tour stuff. But I thought sort of to preface that I would toggle over into a demonstration and show you exactly how this kind of stuff works. So if you bear with me a second, we'll go into the demonstration mode. So this is a piece of software we wrote called Crystal Vision. This is a scatter plot matrix, as you can see. Basically, the large diagram on the right is the one that's highlighted on the left. This is a 5-dimensional data set, and basically it looks like Gaussian elliptical contours. One of the things we can do with this is we can initiate the Grand Tour. And so this is a rotation in 5-dimensional space. It's rotating in 5-dimensional space and being projected into the 2-dimensional, lower dimensional projections. This maintains pretty much the elliptical contours, and so you might suspect that this is just a 5-dimensional Gaussian cloud. I can stop this, and we can toggle over into parallel coordinate space. So this is the parallel coordinate version of this plot. And one of the things you can kind of see is that we have these hyperbolic contours on the edge of this plot. And so one of the things we can see relatively quickly is that we have the analog of an 5-dimensional ellipsoid is something that has these hyperbolic contours. What I would like to do is show you the saturation brushing idea and show you how we can use that to find structure. So what I'm doing is taking down the saturation level, and one of the things you can see once we take, so the idea of saturation brushing is that we have a bunch of points plotted at the same pixels, so they're overplotted. One of the things we can do is take down the saturation level. So where there's very little overplotting, it goes nearly to black. Where there's a lot of overplotting, it will go to a much lower grayscale level. Now, one of the things we can do is edit this. So I'm going to use a clipping tool, and you can see that there's a structure in the middle of this. And so what I want to do is isolate that structure and see if we can understand what's going on. So I'm doing a series of clips, and because we're having fewer and fewer observations now, by the way, there was about 4,000 points in the original picture. As we desaturate it, we get fewer and fewer points, and so I can do this kind of clipping here. And now we see this, this was the internal structure. Let's see if we, it's fully saturated, but the projector doesn't show it as well. A couple of things you can see is that wherever I have a gap in any of the horizontal pictures, that indicates that there's a cluster. So in fact, there's 1, 2, 3, 4, 5 gaps, which says that there's 6 clusters in this data. One of the other things you can see is that there's these crossing points, which indicates that there's a negative slope. And so we have substructure within the cluster that are some linear features that have negative slope. Overall, we have things approximating a thing here. So there's roughly a linear structure here, and this is not quite so spread out, but this is also indicating that there's sort of a two-dimensional linear substructure that we're looking at here. One of the things I can do is I can get a brushing tool out, which I'm going to do, and we can sort of brush these with different colors so we can identify the cluster. So hopefully that's not too invisible on the screen. The color rendition of this projector is not as great as it could be. So what we've done now is identify by color the 6 clusters that are available here. And one of the things I can do is I can initiate the grand tour again. And one of the things we would like to see is that these colors stay close together, and in fact that's the case. And so within the 5-dimensional space we have identified 6 clusters that are essentially coherent as we have the grand tour. So the fun thing about this is that if I put it back in the original and put it back to the original configuration and maybe make the points a little bit bigger, you can see that if we initiate the grand tour once more, this is in fact a 2-dimensional structure that contained the word eureka sitting in a 5-dimensional space. Notwithstanding linear regression methods, I doubt very much that you would find this structure if you were doing a traditional linear regression. Okay, so that's a little bit of a demonstration of how we do that stuff, or how it looks when we do it. So let me try and tell you a little bit about how we do this stuff. So conceptually, what we can think of a mapping T of C, which maps a point x1, x2 into a line. So T maps a point x1, x2 into a line T and f of T. If f of T is 1 minus tx1 plus tx2, this convex linear transformation of the first component into the second component is basically a Lagrange linear interpolation of degree 1. And so that's the basic framework. We can think of this as basically an inner product where f of t is going to be an inner product of the point z with mapping t f of t. We can formulate that actually as a form where f of t is z dotted with n of t, where z is the point in Cartesian space and n of t is this linear transformation vector. The idea, though, is that if we look at n0, that's 1 and 0, and if we look at n1, it's 0 and 1. So when we dot that, the first point will be x1 and the second point will be x2. And so this is just the straight line that joins x1 to x2 in parallel coordinate space. Now, the interesting thing is that we can do all kinds of interpolations of this. The system I described as parallel coordinates now, the traditional parallel coordinates is just this transformation, but we can have lots of different transformations. And so we can generate alternate interpolations that give us different kinds of information. We can also do this with cosines and sines. So we have a polar form of this interpolation as well. So here is kind of what some of the things look like. If we have a slope of +1, in the standard interpolation, these will all be parallel. If we have a slope of 0, that is, everything has the same value of y but different values of x's. So here's the y and different values of x's. We have a slope of -1. We get this central crossing. And if we have a slope of infinity, we get all the same x's but different y's. And so we get, these are the standard parallel coordinate transformations. But if we want to look at some of those other three transformations that I had listed, the other three linear transformations, these are what we see here. And by looking at sort of alternate transformations, we can get different kinds of pictures and get different kinds of interpretation. Again, this is the standard one. The one on the right-hand side is what we get when we do the cosine and sine transformation. And so we can get smooth-looking transformations as well. One extension is to replace the polyline by a smooth curve, and for a number of reasons this is somewhat more appealing. One of the things we would like to do, though, is we would have, like these normal vectors, to have continuous first and second derivatives so that they meet up smoothly. This is a transformation that does that. And if we want to look at, say, for example, 5-dimensional data, this is the transformation for the first axes, first pair of axes, the second pair, third pair, and fourth pair. If we go higher than 5 dimensions, we just start over again, and so we can do this kind of transformation repeatedly. So just to illustrate what this stuff looks like, one of the sort of old-fashioned classic data sets was 1978, 1979 automobile data. It's a 5-dimensional data set that I used in the earliest versions of this discussion in parallel coordinates. It talks about miles per gallon, the weight, the price, the engine displacement, and the gear ratio. So let me show you the traditional parallel coordinate display and the smooth one with the interpolation that I just shown. Now, one of the things that's interesting about this particular piece of data, this data set, there are a bunch of automobiles here with small engine displacement and relatively small weight. There's, relatively speaking, a gap, and there's some high engine displacement and some moderate engine displacement. And you notice one of the features that you see is you sort of get this crossing effect. So the ones that are heavy cars with big engines, this is miles per gallon, and so they tend to have small miles per gallon, whereas the small cars tend to have large miles per gallon. This is gear ratio and price, and what this is basically saying is that we have a hyperbolic contour on this side, but we have very expensive cars generally have very low gear ratios. So this is a parallel coordinate version. Basically, many of the same features hold, but the nice thing about this is that we've structured this so that all of the curves approach the axes in a perpendicular manner. They're orthogonal to the axes, And so it spreads out the one-dimensional views of these things, so we get a kind of a confusing view here, but we get a much clearer view when we're looking at the smooth version of these. One of the things I'll show in a minute, and the question that frequently comes up is, well, this is Wegman, you're talking about weight and displacement and mileage, so I can kind of compare those two things and these two things, but I can't easily compare weight to mileage. I can't easily compare weight to gear ratio and so on. So one of the questions that often comes up when I show this kind of methodology is that people say, well, you know, how do you reconcile the fact that you have this sort of asymmetry in the adjacency? Well, one of the things you can do is permute the axes, and so this is a second permutation of those axes, and so now I have mileage and weight, but I have engine displacement and gear ratio. Price, which was on the bottom, is now in the middle, and so I can do this permutation and get other adjacencies. This is a third permutation of these things. And so, for example, now gear ratio is adjacent to weight, and we can say that gear ratio and weight are clearly inversely correlated, negatively correlated. They have this crossing feature in the middle. And so the idea here is that, of course, if you have a heavy car, you need a low gear ratio in order to be able to overcome them. Overcome the weight of the car. If you have a very light car, you can use a high gear ratio, which gives you much more torque, or much less torque. Another variation that we've done with this is what we call the power projection method. And so if we want to look at Z and N equal to 1, that would give us a linear feature if we were looking at sort of normal linear structure, and that's in effect what we have. But we can do other kinds of combinations as well. One of the things we can do is look at x1 squared and x2 squared. So instead of looking at z, we can look at z squared. In that case, we get z squared dotted with n gives us ax squared plus bx x squared. So we can look at quadratic features. And so we can look at those kinds of higher order structures as well. So here's an example of what we do. If we have the standard linear one and we have the cosine sine interpolation, so if we have standard linear ones, we can get the crossing that gives us a negative slope. If we have standard linear here, we get a distinction between the two, and if we look at the crossed version of this, we get clearly distinct views. If we look at the cosine sine, this is the set of things we get cosine sine, and so we can get sort of by looking at these different interpolations, we can see things that we might not see otherwise. So for example, if we have two circular features, this is what it would look like in the standard linear feature, and this is what it looks like if we use a p equal to 2. So we can, by using variance of the interpolation, we can see different kinds of structure. This is one of the things I said before was that if we have a circle, if we have a spherical kind of structure, that maps into a hyperbolic feature, and so this is the standard parallel coordinate display with a hyperbolic feature. Hyperbolic, if we use the second order structure, we get the single crossing in the center, and so we can, by looking at what we call the power projection method of second order, we can get quadratic features to linearize and look just like things that we would have linear structures in ordinary space. So as I said, one of the common questions is, what about this adjacency issue? How do we deal with axes that are not adjacent to each other? And the fundamental question is, how many parallel coordinate displays do you need to see all pairwise adjacencies? We actually deal with this in a couple of ways, but one of the interesting ways is, well, this is what I said before. If I order my axes 1 to D, I can compare 1 to 2, 2 to 3, and so on, but I can't compare 1 with 3, can't compare 2 with 5, and so on directly. So one of the things so this is a kind of a cute algorithm for finding permutations so that all possible pairwise adjacencies are held. So suppose I have 7 dimensions here. What I want to do is create this zigzag pattern. So I put 1 adjacent to 2, 2 adjacent to 7, 7 adjacent to 3, 3 adjacent to 6, 6 to 4, and 4 to 5. So that gives me this permutation. I can, essentially the idea is that I want to rotate this permutation. So the next one would be 2 with 3, 3 with 1, 1 with 4, and so on. And I've illustrated that here in a 6-dimensional case. So the first permutation is the dashed line. It gives me 1 with 2, 2 with 6, 6 with 3, 3 with 5, and 5 with 4. That's this permutation. If I rotate it, the second one gives me 2 with 3, 3 with 1, 1 with 4, 4 with 6, and 6 with 5. That's the second permutation. The third one is the dashed line. It gives me 3 with 4, and so on. And as soon as I do the third time, what I get is a complete graph. And the complete graph tells me that I have all possible adjacencies. So we use this little trick to get all possible adjacencies. So that's how it works graphically. And if you sort of write down the algorithm for doing this, this is the formulation for getting the sequence of numbers. And if you combine that with the greatest integer function, this is the sequence that gives us a zigzag pattern. And I can do that as soon as I get a complete graph. And I won't make you read all that stuff, but this is sort of the bottom line. If I want to get all possible pairs, then I need d plus 1, the greatest integer in d plus 1 over 2 number of plots. So basically d over 2 plots. So if I'm in 10 dimensions, I need 5 plots. If on the other hand, I wanted to look at a scatter plot matrix and I want to look at all possible scatter plots, pairwise scatter plots, I would have d choose 2. So there are far fewer plots needed in parallel coordinate space than are needed in Cartesian scatter plot matrix space. This has the advantage that if you're using scatter plot matrix and you have a lot of observations, a lot of dimensions, the scatter plots get very tiny and it's hard to see anything. Okay, I'd like to toggle over to the idea of the grand tour. So the notion of a grand tour is that if I want to understand an object, I don't look at an object from one static perspective. What I do is I move it around and look at it from all possible angles. So hence the notion grand tour. I want to be able to look at my point cloud from all possible angles. But the angles that I'm talking about are not angles in 2 or 3 dimensional space, they're angles in high dimensional space. So the question is, how do we do that? The original formulation of this is the so-called torus method, or what's often called the winding algorithm, and I'm going to describe that in a minute. But the notion is as follows. Suppose I start off with a rectangular structure. So I'm just looking at a two-dimensional rectangle. What I want to do is identify opposite sides of the rectangle. So I can take my rectangle and fold it up into a cylinder. And then what I want to do is fold my cylinder into a torus. Okay. So the basic idea conceptually is that we want to look at a two-dimensional torus embedded in 3 space. So what I want to be able to do is I want to think of unfolding that temporarily into the rectangle. What I want to do is I want to start drawing a line that has an irrational slope. Okay. So if I draw a line that has an irrational slope and I get to the upper edge, I come back down to the lower edge, and I continue like that, as long as it has an irrational slope, that line will never repeat. So it will eventually be a space-filling line on the surface of this two-dimensional torus. Okay, now what we want to do is we want to generalize that to higher dimensions. So instead of looking at a rectangle, I want to look at a hypercube, and I want to identify opposite faces of the hypercube. So if I have a regular cube, I have 3 pairs of opposite faces. If I have a 4-dimensional hypercube, I'm going to have more, right? I'll have, 5 pairs of opposite faces, and so on. So that's the fundamental idea, and instead of, so the reason it's called a winding algorithm is it's winding around the surface of the torus. In hyperdimensional space, it'll be winding around the surface of the hyperdimensional torus, embedded in one greater dimension. So let me describe how that works. So we want to look at the canonical basis vector Ej, where the 1 is in the jth position. So the Ej's are the unit vector of the coordinate axis in the initial position. So basically, when we do this grand tour, we want to do a rigid rotation of these axes into a new position with new basis vectors Aj, depending on t. So t, as time goes on, we want to rotate this coordinate system. And the idea is that we're going to project the data into the new coordinate system. So that's essentially a coordinate transformation, but we visualize that as a geometric transformation in what I did before, when we illustrated that before. Okay, so what we want to do is we want to take each of the original observations and take the inner product with the rotated coordinate system, so that will project that new point, that old point xi, into the rotated coordinate system. And so we can essentially do this coordinate transformation by rotating the coordinate system. We can do this coordinate transformation and project into this newly rotated system. So if x is the original vector and y is the rotated vector, then we can compute y by looking at essentially the dot product between the x and the a vectors. So that's essentially what that says. If y is a linear combination of basis vectors representing the ith data point in the rotated coordinate system at time t, one of the things that's worth pointing out is that yi of t is a linear combination of the data. And so if one of the components of the vector is held out from the grand tour, so we can do a partial grand tour, there's no reason why we can't hold one of the coordinate axes fixed, then that partial grand tour lends itself to interpretation as a multiple linear regression. Essentially, we're writing one fixed coordinate in terms of the other not fixed coordinates. So what we want to do is to find a general rotation Q such that Q will map E, J into AJ, And so we can conceive of Q as either a function on the space of basis vectors, or more interestingly, as a D by D matrix where E with Q, E multiplied by matrix Q gives us the rotated coordinate axes. To do that, we want to think of Q as an element of the special orthogonal group SOD, where we're looking at D by D orthogonal matrices having determinants +1. And so in order to accomplish this grand tour, what we want to do is find a continuous space-filling curve through SOD. So instead of looking just at, instead of the winding algorithm, we're going to first of all do a structure that we do a space-filling path through SOD. By the way, the grand tour has, when we talk about the grand tour, it has two critical features. One of the features is that we want the coordinate system to move smoothly because we want to have visual continuity. So that's why we want to have a smooth transition. We also want it to be space-filling, and the reason we want it to be space-filling is obviously that we want to be able to see all of the possible orientations of the coordinate system. So we want to look at it from all perspectives. Early on when this was discussed, there was some discussion of the Andrews curves being a space-filling system, but in fact the Andrews curves are very far from being a space-filling system. So we want to construct a composite mapping from the real line into the p-dimensional hypercube, so 0 to 2 pi raised to the p. So alpha is a mapping from R into that hypercube. So we want to take the components of alpha of t to be our angles. So the mapping from beta to 0 to 2 pi p into SOD is given by this. So we construct a mapping that maps all theta 1, 2. Theta 1, 2 is going to be rotation in the 1, 2 plane. Theta 1, 3 is the rotation angle in the 1, 3 plane. Up through theta d minus 1d is rotation in the d minus 1d plane. So R1, 2 is just going to be the rotation there, and we just multiply these rotation matrices out to get the generalized rotation matrix. So this Rij is going to be a matrix of the following form. It's one down the diagonals, except in the ith row and jth row and ith column and jth column, and it will have the cosine minus sine, sine, cosine. So essentially what these are doing, what this rotation matrix does is it rotates individually in each of the pairwise planes that make up our d-dimensional space. And remember, it's probably obvious to say this, but in high dimensions you cannot rotate around an axis, you have to rotate in a plane. Because there are many orthogonal axes to a given two-dimensional plane in high-dimensional space. So we have to rotate in each of the planes individually. These angles, theta ij, are called Euler angles. So we construct the mapping alpha of t as just lambda 1, lambda 2, lambda p, each multiplied by t as a mapping from R into 0 to 2 pi hypercube. Lambda jt is taken modulo 2 pi, so we want angles 0 to 2 pi. The lambda 1s through lambda p are taken to be linearly independent real numbers over the rational numbers. So this is the idea, this is the analog of the idea that we want to have slopes that are not linear combinations of each other. The slopes have to be linearly independent because if they're linearly dependent, then we start repeating. That's the same thing as having a rational slope. Okay. So by doing that composite, we can construct the winding algorithm, and we can look at a hyperdimensional torus, and we can find a smooth path through SOD. Now, one of the criticisms that is made of the winding algorithm is that because it has irrational slopes involved, it can go on forever. And depending on how the lambdas are chosen, it can get stuck in certain regions of the hyperspace. So it's not always the case that you want to be able to do this exactly. And one of the things that we've been developing is the idea of looking at fractal curves. So curves that can repeat. So here is a 3 cube basically, and here's a Hilbert path through the 3 cube. And the idea is that as we can connect these Hilbert paths up, and so in 3 space we take 8 of these things, reduce the scale by half, and fill up the 3 space, and that puts all of the points closer and closer together. So as we do higher and higher fractal curves, we can pass arbitrarily close to any point by doing sufficient number of refinements of the fractal curve. We can do this in, there's analogs of these piano curves and Hilbert curves in multidimensional space as well. This is a 2-dimensional piano curve. We can have multidimensional piano curves as well. So another way of doing the grand tour, the fractal tour, is to do it with, instead of looking at a path through the cube, look at a path, the fractal path through the cube. How am I doing on time? Got 15 minutes? Okay. What I'd like to do is show you a couple of examples of how we can use this kind of stuff iteratively. And so one of the interesting examples we came across was this sand data from Ramsay Island in the Scotch Hebrides. So this apparently has been one of the interesting discussions that has been held in the archaeology literature and the early archaeology literature, I guess. So in the Middle Stone Ages, Mesolithic, which is about 10,000 BC, it was discovered that there are a number of archaeological sites where basically trash was buried. Midden is basically a trash dump that the Stone Age guys put their junk, and so the idea was that these were buried under the sand, and the question was whether the sand below the midden was beach sand or sand from the upper layers of the dune sand. So the idea was that if the sand below the midden were beach sand, then that would say that these people sort of lived on the beach. If it were dune sand, that would say they were living in the dunes. But now this sand is on the beach. Now these middens are on the beach, so it would indicate a shift in the coastline over the years. So this is the idea that would indicate a seaward shift of the beach-dune interface. So one of the things we'd like to do is be able to cluster the samples of modern sand into beach-like sand and dune-like sand, and classify the archaeological sand samples as to whether they were beach or dune sand. And then we could verify the hypothesis that there was a shift. So the historical approaches to these were to fit parametric distributions and compare the modern archaeological sands to dune sand, and the modern and archaeological sands based on the values of the parameters associated with that. So people have tried Weibull, log normal, log hyperbolic, log skew, Laplace, Barndorf-Nielsen did some stuff in 1977. So these models all had 2 to 4 parameters. Theory was developed, but the practice turns out to be relatively problematic. So this is a picture of the transects that were done. There were several sets of transects here going from what is now water to what is now dune. And this site is called the CC site. I'm not going to attempt to pronounce it. There was also transects done down here, which was a different location, but basically not too far away. These transects were all combined originally, and the parametric models were fit. So this is a parallel coordinate plot of these things. The black ones are the CC sites, and the red ones are the CNG sites. And one of the things I told you before was that if you have a big gap in the axis, that indicates that those are substantially different clusters. So in fact, the combining of these two different sand samples was not a good idea. I should tell you what they did, by the way. What they did along the axis, there are particle sizes. So they would take the sand and put it, first of all, in a relatively coarse mesh and shift it, adjust it so that the fine particles went through and the coarse particles stayed there. And then they would have an increasing set of refined sieves. And so this is the finest sieve, and this is the most coarse sieves down here. And so the CNG site tended to have relatively coarse stuff and relatively little fine stuff. So this is the weight in grams. I don't think that's me. This is the weight in grams of the relative sites. The whole set, where's my guy? The whole set of these things, I'm sorry, it's died. The whole set of these things weighed 60 grams, so they took 60-gram samples and then sieved the 60-gram samples. Anyway, the idea was that we combine the parallel coordinate display with the grand tour and use what we call the brush tour strategy. So we brushed out obvious clusters. We brushed out obvious clusters by recognizing the gaps in the horizontal axis. We brushed them with colors, and we executed a grand tour until a new cluster appears. We brushed it again and repeat that until we don't get any more obvious clusters happening. So this is the sequence of things we did. We took the original CC data. We filtered out the red ones. We left everything else green. We did a grand tour. We filtered out some ones we colored blue. The rest were left green. We did magenta, cyan, and so on, until we had red, blue, magenta, cyan, yellow, and green clusters. So this is what happened. It turned out that red and magenta were dune sands, and the other colors were beach. So magenta is up here and red, and you can see that magenta and red pretty much separate from the other colors. Blue is very different, but the other colors are different. And so we can believe that we can just visually separate these types of sand from just a visual perspective. Oh my, this is not so good, but I'm not even going to try that. So then we overlaid the archaeological sands, the sands from the bottom of the middens. And those are colored white, and it turns out that the white ones pretty much follow the red and magenta, except here at this scale. It turns out that the white and the red are very different in this perspective. So the conclusion is that if you were going to try and characterize these, we did a density plot. So this is what the dune sand plot looks like. This is the midden sand, this is the archaeological sand, and these are the beach sands here, these two local modes here. So if you had to characterize it, you would say that the midden sand looked more like the dune sand than the beach sand, but it was clearly a distinct structure that was different from the dune sand. So here is some conclusions. Sands from the CC site and CNG site have considerably different particle size distributions, and you really can't effectively aggregate those. I didn't point this out, but data at small and large particle dimensions is too quantized to be used effectively. So you really can't use, the idea is that there's very little sand that is big particles and very little sand that is very fine particles. And so when you weigh these out, you get a rounding error on the grams, and the rounding error is too quantized to be able to use that. So when we did this stuff, we did a partial grand tour. We didn't include these things where the particle sizes were either too big or too small. So the brush tour strategy is effective at doing the clustering. The conclusion is that the midden sands are neither modern beach sands nor modern dune sands. They are more similar to modern dune sands, but the result does not support the seaward shift of the beach-dune interface hypothesis, which is common in the literature. And so this suggests the middens were always in the dunes and not buried in the beaches, and the dunes shifted over to the beaches. And that's not the view that's taken in the standard literature. I have 5 minutes. This is an interesting data set from the point of view that it was a British bank. I deal with Scotland and Britain here. This was a British bank that failed. So I guess probably these days we should talk about American banks and bad loans and whatnot. But anyway, it's interesting because if you multiply 8 by 132,000, we're talking about essentially 1 million numbers. And so this is a relatively large data set from the NP perspective. So this is the profit of the bank. This is the age of the customers, the years that the customer has been in. This is occupation of the customers. This is the months. This is the residency status, marital status, and gender. What we've done here is we've colored all of the customers that made a negative profit for the bank red and that made a positive profit for the bank green. And of course, red and green added together in an additive color system make yellow. So wherever it's yellow, it's essentially neutral. Now, you cannot discriminate on age. You don't know how many years the customer is going to be with the bank. You have to be very careful about occupancy, number of months lived in a residence. But one of the things you can see is that young people tend to lose money for the bank, and old guys tend to make money for the bank. So and of course, residency status, marital status, and gender are categorical variables. So even though strictly speaking we're not dealing with, we're really interested in integer variables. That's because there's a lot of overplotting. Okay, and so what we've done is just do a teeny bit of the grand tour and just spread this stuff out a little bit. And once you start doing the teeny bit of the grand tour, you can see some features. For example, here is a residency status, marital status combination that is essentially red. So this tells us that people that have this residency status and this marital status are probably not good for the bank. Here's another group that is slightly red. And so one of the things, and here's some more stuff that's red in here. So the idea of the prune tour strategy is that we want to formulate a tree structure, and what we want to be able to do is say, okay, if you have this linear combination of variables, you're probably a bad risk for the bank. So you're not basing it on their age or their gender or their residency status or their marital status, but it's a combination of those things. So you can probably get away with doing that. So you prune those things out, you prune the red things out, and then do a little bit more of this grand tour. And you can sort of sequentially do this, and you start seeing that you have some greens here and some red structure here. And so if I continue this brush tour, I continue to prune and continue this strategy in general. And as I prune more and more, I get fewer and fewer observations. So this is going through, I guess, 8 tour prune steps, and we've gone from 132,000 observations, so there's only 5,700 left in this. And of course, because there's fewer and fewer observations, there's less and less saturation, so it mostly looks black against a white background. Okay. So anyway, when we did the analysis, we were able to hand the bank a tree that essentially they could follow through, and it was a decision tree on what customers they should take risk with and what customers they probably shouldn't take risk with. This was another application that we applied the grand tour technique to images. So instead of looking at linear combinations of data points, we looked at linear combinations of images with the same grand tour technique. So this is at the Naval Coastal Systems Center in Panama City, Florida. This is a minefield. You can see there's a few white dots here. Those are mines, as they say in the Navy. Those are proud. They're sitting on the surface. There are other mines that are buried, but you can't see them. What they did was they overflew this field with a camera that was sequentially exposing pictures in various filters, and so they got 6 different filtered pictures. And so one of the things that happens is you can see some in this filter. In this filter, essentially they disappear. This is a linear combination that we picked up from doing grand tour. And one of the things you can see is this is the set of original mines, and you can see a second set that is sort of one row back, and you can see another set that's another row back. And there's a few odds and ends here and there as well, but essentially there's 3 rows of landmines. So this is a completely hands-off way of detecting these landmines. And by the way, this is a typical pattern that if you want to structure a minefield so that it deters people from trying to get through, this pattern is the pattern that you want to use, because if they get through the first round, they will hit the second round. This is a pattern that is typically used in sort of a benign use, if you can call using landmines benign. It announces to the people that this is a minefield and you don't want to cross it. If you're really interested in maiming and hurting people, you put them at random so that there's no, so to speak, warning. Last 2 examples. These are some petroglyphs that were taken in Texas. This is a rock face, and believe it or not, there's an image in there. This is another rock face. It has initials HC, but there's an image underneath there that you probably can't see. But again, we converted to RGB and then did the grand tour on the RGB. This is what the screen looked like, but when we enhance it, you can see that this figure. It's essentially a male figure with long hair. It has arms. There's actually a knife in the hand here, and you can kind of see the legs drawn there. So that we discovered, within 30, 40 seconds. This is the one with HC on it. This one has short hair and is wearing a skirt. This is a female figure. Okay. She says stop, and so. Yeah, part of what I was saying in the beginning is that we can use a different normal vector when we do this. I don't know if you were here in the very beginning, but there's a way of doing that that you can have alternate presentations of the parallel coordinate axes. The other thing that we do in terms of permuting the axes themselves is that essentially when you do this grand tour, you're taking orthonormal linear combinations of the original data axes. And so essentially when you do that, if you let it run for a while, it's going to have all possible permutations of the axes. And we found that by just essentially doing the grand tour and watching it for 2 or 3 minutes, that seems to capture a lot of the information that allows you visually to capture a lot of the information that's in the parallel coordinate axes. I don't know if that's a good answer, David, but that's my answer.
Follow up in one way. Is there happening for a while experience look at it? Get some idea of what makes the plot interesting. Is there anything parallel
Yeah. Actually, in our original discussion, we had some clues as to what kind of things that you can see, but you can see, there's separation, which allows you to see clusters relatively quickly, and those clusters show up in a nice way. The crossings indicate correlation. It turns out that if you look between any pair of axes, the number of crossings of the linear components are proportional to Kendall-Tau correlation coefficient. So you can actually have some idea of what correlations are involved as well. I have illustrations of a lot of those things in some of the earlier works that we've done. So linear structure, some quadratic structure, nonlinear relationships, cluster structure, all of those things, if you sort of train a little bit on what parallel coordinate duals look like, it's relatively easy to see those things. People always say to me, well, everybody understands Cartesian coordinates, but these parallel coordinates, they're not so easy. But, they teach Cartesian coordinates in grade school, and they don't teach parallel coordinates until you get to Newton Institute, maybe.
So when you were doing this tour of special orthogonal group, then isn't the way that you chose to do it tending to, it's not kind of uniform I mean, you gave a special role to the axis number 1, and that would tend to give you more points of view, I think, from the same direction. I don't know whether maybe it makes
Well,
a difference in practice, but
if
I would
I
have
do-
thought that if you try to do something that spread out uniformly over the special orthogonal group, you might be able to detect.
Yeah,
what
there's
they
actually
pick up.
not a preference. It really depends on how the slopes, the lambdas, are determined originally. There's no preference for the first axes, but that's why we did the fractal tours. The fractal tours have the ability to sort of go through the hypercube sort of in an even way. So.
Yeah, but what was it? Just a question of the hypercube? I mean, there's also. Well, I'll talk to you about it
Okay.
privately.
Okay, let's just now have tea until 3:30, and first thank the speaker again.